Okay, good morning everybody, and thanks very much to Jain University for this opportunity, especially Professor Asha, Professor Reddy, Professor Anu. Thanks so much for your hospitality and for having me here. And it's so nice to speak to a whole room of young faces. So let's go on and talk about the life history of a raindrop. So before I start about like one specific raindrop, let me find out how many of you are incredibly anxious about climate change in your lifetime. Large numbers. How many of you are vaguely anxious? Not too anxious, but little bit. Yeah, a few. How many, is there anyone who's not at all anxious? One. Good, good. Oh, a few. So you're not at all anxious about climate change. Great. So yeah, let's go on and see. The basic point, the point I've come here to drive home is just one thing, okay? This is an open problem. Climate is an open problem. Indian monsoon is an open problem. We need people from all backgrounds, like you can be physics, chemistry, engineering. You can be from even humanities or other subjects. There's so much to be done on the Indian monsoon. There's so many PhDs to be gained in this. Like this is one field where you don't have to go and search for an open problem. Every problem is open. So it's very good if young people like you get interested in this problem, and then you also tell your friends to study this or to consider this as one of your future options. So life history of a raindrop, let's start out with that. Okay. Okay, so this is the work of S. Ravichandran. He's my recent PhD student. I put a doctor in inverted commas next to his name because he's not yet technically a PhD. In fact, his defense is on the 2nd of August. Namely Wednesday. So if he passes that, we'll take the doctor and put it here. So this, I will mostly be talking about general things about a raindrop, but I will touch upon his work quite a bit. There are also like 2 new postdocs in the department, Jason and Priyanka. So they have started looking at cloud flows. All of us, all the names here are interested in cloud physics. My colleague is Samriddhi Sankara Ray, with whom I discuss a lot. And there's also Deepu, who was a recent postdoc, who is now faculty member in IIT Patna. And Lokahit is a young student from ISER Pune who is spending 1 year. He's just started again on this problem. Okay. The Indian monsoon. How many of you think the Indian monsoon is special? Okay, why do you think it's special, anybody? Yes, like 1 billion of us depend on the Indian monsoon. Like if the monsoon fails, we're in deep trouble. And like normally when you say drought, you actually mean that, you say this year is a drought year, you actually mean the rainfall was 90% or less than its usual. You do not mean it was a very poor rainfall year. So every year we get rainfall till 85 centimeters. There's enough rainfall to cover India for like almost a meter. And then if that falls by this much, we call it a drought year. So like if rainfall goes up and down by 10% or 1 standard deviation, then we already are in trouble. Imagine if it started changing quite a lot more than that. In the last 120 years, that has never happened. It's a very, very, very dependable phenomenon. So, and we know that it's not the last 120 years. We have rainfall data for the last 120 years. But we know about the monsoon from lots of writings. Like even the Arthashastra deals with, that was written in the BC, and it deals with how, you have to get prepared for a bad monsoon year. So this has been going on for at least 2000 years to our knowledge. The first reference to the Indian monsoon that I saw was in Ahananuru, which is a Tamil text, which was somewhere between, it's not dated very exactly, but 600 to 300 BC. So there's a very clear description of how the earth changes from this thing, sometime in May to this thing sometime in July. So this is a very, very big dramatic event which doesn't happen in many places in the world. It doesn't. Like if you go, to the north of the tropics, like if you go to Canada or America, you will get seasonal changes due to summer and winter. But you do not get this kind of melodramatic change in the rainfall. So this is very, very special. And so every year we wait anxiously for the monsoon. So, and obviously because it's, such a dramatic event, like literature, like there's so many poetry through the, through the centuries which have been written. It's not playing. So people have written rags on the rain and all of that. Okay, so let's start with the water cycle. This is something you all have seen in high school, right? About the water cycle. So you know what it is. Basically, from the ocean, from rivers, from groundwater, we have evaporation. And that evaporated water goes in the form of water vapor to high up in the atmosphere, where it condenses again. And the condensation comes down as precipitation or rain, or snow, or a variety of other things, ice and snow. So then there's also fog and dew. And all these things go back into groundwater, river water, and then the cycle continues. Okay, so this is basically the water cycle. And for people who are not very, very anxious about climate change or any man-made change, I would strongly advise that you start getting anxious at least about this part, because our groundwater resources are so depleted in the country over the last couple of decades that our rivers are not flowing. Our rivers are not flowing as they should. Groundwater is not just for sitting under the ground and for us to pump out. It's also a very essential ingredient in river. So then with Himalayan ice decreasing and groundwater decreasing, we have to think about ways of, doing things better. So what I'd like to emphasize there is that even in a drought year, we may get not this much, but this much of rainfall. That's actually enough for all of us, if we manage it well, if we are sensible about it. So this water is going to be a very, very, very important thing in the coming decades. Okay, so let's take up, we're talking about the life history of a raindrop, right? Let's start from here, to become a raindrop, to become this guy. This cycle has to start, and a lot of things have to happen before one raindrop can be born. We're not even talking life history, we're talking before the birth of the raindrop. So here's the oceans. On a hot day, it evaporates. That part is easy. That part is easy. So you now have on the surface of the ocean, you have a big puff of evaporated, a puff of air which contains a lot of water vapor. It is a little bit warmer than its surroundings, so it's a bit lighter. Also, because it contains water vapor, it's a bit lighter, but the water vapor is, actually the water vapor content is very, very small. I'll ask you to go home today and check how much water vapor is there in a 1 kilogram of air on the Earth's surface. How many kilograms of water vapor? Any guesses? Yeah? 1 milligram. Yeah, so in 1 meter cube of thing, it's about half a gram on a rainy day. On a very, very rainy day, the biggest amount would be half a gram. So on normal days, it could well be in milligrams. So then this thing is sitting there, it's now going to rise slowly because it's warmer. So it's warmer, it's lighter, so buoyancy is going to make it rise. So that looks very nice. It's rising. But how far can it rise? How can it rise? For a cloud, you need it to rise through several kilometers. Have you seen chimney smoke rising through several kilometers? No way, right? No way. You see here it's already gone. So this chimney must be maybe 100 meters tall, this may be 50 meters, gone. It didn't rise to even 1 kilometer, let alone become a cloud. So this is smoke coming out of an industrial chimney, which is coming out with a large amount of momentum, and that itself is gone. This is like basically a hot puff. The smoke is lighter than its surroundings. How can a cloud climb several kilometers? That's the first question, right? So like just with its tiny amount of buoyancy here, it's not like got momentum like this chimney smoke, and still like this little thing can climb for many kilometers. For that, you need a convergence. So what a convergence is that you have winds coming from two sides or from all sides, more than one side. So the incoming wind at the ground level is large. So the only way for it to escape is to go up. So by the equation of continuity, it has to go up. And so you need this reasonably strong updraft. That's the first criterion. So like you can actually do calculations. Updrafts are actually very weak, you know. On a very windy monsoon day, the wind may be at tens of meters per second, but the updraft is going to be much lower than that. Okay, and now so you need whatever it be, like this gentle updraft you need, which will take it up several kilometers. So if you look at this radar image of a typical tropical convection, so you can think of all these colored regions as actually cloud, because this is some measure of liquid water content, and the red means lots of liquid water and purple means less liquid water, white means very little. So this height is 17 kilometers. This is 0 to 17 kilometers above the ground. How big is the atmosphere? How thick would you say is the atmosphere? Earth's atmosphere? 15 approximately. That's a good number. So this is reached all the way. So these are tropical clouds, okay? These are not like the usual cirrus clouds which happen elsewhere in the world. Only in the monsoon region, monsoon belt, you get deep clouds like this, which start from, let's say, a kilometer or so and go up all the way. Okay, and this distance is around 750 kilometers. So these are actually large large aggregations of clouds. So this is the first thing that happens. You need this updraft, without which nothing is going to happen. You need many more things, but I'm simplifying it a lot. I'm actually giving you a kind of caricature story of a raindrop. So you can realize that in every statement I'm making, it's not completely precise. There are exceptions and there are assumptions that I'm making to say that. But just to give you the basic idea is what I'm doing. Okay, so then this is a typical cumulus cloud, cumulonimbus cloud we call it, and this is the troposphere, which this is about 10 kilometer. Oh, the 10 kilometer came down, it should be sitting there. And then this is the temperature in the atmosphere. When you fly in a plane, at what height are you? They've drawn a plane here for your convenience. It's at the 10 kilometer line approximately. Yeah, so what's the temperature there? Minus 40. Yeah, very good. Who said that? Yeah. So yeah, minus 40 is a very good estimate of what the temperature is there. So like just as a homework exercise, go home and ask yourself, when I'm sitting inside a plane, I feel about the same temperature here as there, right? I feel like reasonably okay inside. Certainly it's not minus 40 inside. So is in the air conditioning of the plane, are they, changing from cooling to heating? When you go up there, is the thing like automatically somehow changing from cooling to heating and keeping the temperature magically uniform? Ask yourself. I'm not going to answer that question. So what really happens in a plane to give you a comfortable temperature. So this is how the temperature falls. You can't read the numbers here, but this is minus 40 to minus 60. You can say it's falling approximately linearly in the atmosphere. And this fall of the temperature is crucial to our existence. It's crucial to the formation of clouds and to the formation of raindrops. So if this temperature, decrease was not there, we would have no rain. So many things are colluding to help us, like it's incredible. There is this line called the lifting condensation level. You can see that there's no cloud below it. but above it, it's almost like, a flat place above which clouds can form. And clouds can become very, very tall. Here too you see a lifting condensation level. So that place is different for different clouds. I said, like there's evaporation and there's this puff which contains some water vapor which is rising. Different puffs can contain different amounts of water vapor. On a hot day, it will contain a different amount. On a cold day, it will contain a different amount. Its buoyancy will be different on different days. Its upward velocity will be different on different days. So many things are there. Till now, like this guy who's just a bunch of water vapor cannot even dream about becoming a raindrop. Only the lucky guys among these who can go up to some height can start dreaming about becoming a raindrop. Even them, they're still dreaming. We'll come to that. They've not become a raindrop actually. So then here these guys, what is the first thing they need? They need not to lose their water vapor by the time they reach that height. If they keep mixing with the external ambient and dry air and wet air keep mixing, it will always stay unsaturated. In order to condense, you need to be supersaturated, right? Yeah, you need to be supersaturated. And the lucky part is the saturation density of water vapor, or the partial pressure of water vapor for saturation keeps falling with the temperature. So at cold temperatures things condense easily. At warm temperatures things don't condense easily. You know that when you open your fridge and take out a vessel, you see like water droplets on the top of the thing, right? So you know very well that if it's cold, it's going to condense easily. So then it's cold up there, that's the lucky part. So it's going to condense. So the saturation vapor pressure keeps falling as a function of temperature. So depending on the water vapor I am carrying, I am a puff of hot wet fluid who is rising. Depending on the amount of water vapor I am carrying, I will get saturated at a different height. Is this coming out clear? If I am carrying a lot of water vapor, then I can start condensing at a lower height. If I am containing less water vapor, I have to climb to a colder place before I can condense. Yeah? Yeah, so then because of this, there's no one lifting condensation level. I cannot say 1 kilometer is the lifting condensation level. It depends on whether it's a hot day, cold day, how much you have, what is going on, how much you're losing, all of that. So then, in order to reach the lifting condensation level itself, only the lucky guys have reached there. So remember that. And then once you reach that height, can you start condensing? Is the wetness enough? So this is the thing that you want to ask. Can you start condensing just because you've reached a place which is supersaturated? The answer is a big no. And we'll come to why. Okay, then you've reached this height. Condensation will occur only if aerosols are present. And aerosols can mean anything from tiny, tiny particles of sea salt, which can actually climb to great heights, dust particles, and even man-made pollutants, things like that. So only when you have all these things can condensation occur. So does anybody know why? Can you say who's that? Perfect. So they act as sources of nucleation. And why do you need sources of nucleation? Yeah, so the point is, when you study this in physics, you'll think, oh, wait, the minute I'm supersaturated, I'll spontaneously become a water drop. Here am I, a water vapor bunch, and I'm going to find myself supersaturated and I'll spontaneously become. No. In order to spontaneously become a liquid drop, I need to be 700% supersaturated. And that never ever happens in the atmosphere. We're always like 2%, 4%, maximum 4 to 5% supersaturated. We're not going to be 700% supersaturated. Therefore, we need aerosol particles. So if these particles were not all over the atmosphere, we would have been in deep trouble. So before you start thinking that we guys are helping it along by putting pollutants, wait a minute. Yeah, so don't think, let me put more pollutants and get more rainfall. It's not quite like that. And I'll come to that in a minute. If I forget, remind me. Okay, so then you need all these guys. And there is this special radius called the Kohler radius. So the thing is, when you have a very tiny particle, in order to condense onto that very, very tiny particle, the supersaturation itself is a function of radius. It's not a function of just the temperature. It's also a function of radius. So for small particles, the same thing which is supersaturated here will be subsaturated. So it will not coalesce. So there is a particular radius above which it can start growing. Otherwise the same level of supersaturation will start evaporating. The droplet will start evaporating. So it will not grow big, it will shrink and die away. So you need aerosol particles which are bigger than the Kohler radius. Again, don't ask me for a number for the Kohler radius. It depends on your levels of supersaturation, it depends on your temperature and several other things. So then if you have a much more supersaturated environment, then even a small drop can act as a nucleus. But if it's not that supersaturated, only bigger drops can act as cloud condensation nuclei. So we need these nuclei to be bigger than the Kohler radius AK. A is the radius of the aerosol or the raindrop or the cloud drop, whatever. So then you need supersaturation. You need these raindrops. Supersaturation is given by this formula. Who knows what this is called? Clausius-Clapeyron? You've studied it? Yes or no? Yes. So this is basically the Clausius-Clapeyron relation. So I mean, already you're seeing like this chemistry, physics, everything coming into this. So this is the latent heat, this is the gas constant, and this is the reference temperature, and this is like the temperature you're sitting at. So the colder you are, the easier it is for you for your vapor concentration to cross the supersaturation. You can work this out by the Clausius-Clapeyron equation. Given this, you can write down a formula like this. You have to use this and many other things and some 2 pages of derivation. It's not very hard. Even an undergraduate can easily do it. You will get this equation for the radius, for the growth of the raindrop. I will not call it a raindrop yet. I'll call it a cloud drop. And I'll tell you why. So here is my cloud drop. It has satisfied these 2 conditions. It's climbed up. It's done all those things you asked it to do. And now it has to grow. So what is the rate of growth? You can ask yourself by knowing the C, this value C in MK's units is about 10 to the minus 7. And this is the density of water, density of vapor, and everything else I've defined. So you can actually, solve this equation. Can you solve this equation? Yeah? If everything on the right hand side is constant, you can directly write the solution, right? Agreed? Yeah, but everything on the right hand side is not constant, that you have to worry about. Like as the drop rises or falls, rho s itself is changing, rho v is changing. So you have to worry about what it does as a function of height. So height comes into this equation, although it's written only in time. Okay, thus we've summarized what we talked about till now. A cloud drop is born. It's just now born if a hot wet puff formed on Earth's surface, and preferably this is not just one isolated puff, but it's a continuous process, like evaporation is going on and on. So instead of a puff, I'm getting a tower. I'm getting a column which is rising. Okay? And this was lifted by enough of an updraft, and I told you updraft is due to convergence of winds, and that's why like you always have this happening in the equator. You can ask yourself why. There's a lot of cloud cover in the equator. And then all the time it rose through those kilometers, it didn't lose its water vapor to the neighbors, it attained its lifting condensation level. And then it found an aerosol particle bigger than the Kohler radius. So when it satisfied all these conditions, it became a cloud drop, not yet a raindrop. Remember, in the life history, we've not yet come to the place where it's born. The rest of its life is, the major challenge is in becoming a raindrop. The rest of it will come easy. So with all this lecture, you would have got the idea that, oh, it's a very, very tough thing. Like it's a very rare occurrence. Like normally a cloud drop can never form under normal circumstances. That actually is not true. I don't want you to go home with that impression. This is a world map. I'm going to show you about 2 years of cloud cover. So already in the still picture, everywhere you see white, it's covered by cloud. Everywhere you see blue, the sun is shining there. Okay? So then you'll see that this is, what is this? Sahara. Sahara will always be, never have cloud cover, poor thing. And some of Arabia also. And watch India. India is right now similar to Sahara, but watch it as this movie goes on. So what you can see here is that, on an average day, like 70% of the earth is covered by cloud of some kind. So it's not that rare an occurrence. It's happening all the time. All these conditions are being fulfilled and this cloud cover is happening. Let me play the movie which runs over 2 years. And you will see like what happens in the monsoon season in India. So just watch India as you watch this movie. You see? This is more than 2 years, several years. So you see the monsoon coming and covering India, going away, covering India, going away. Yeah? So this is basically the cloud cover. So now we understand why this is an important problem. This is an important problem because cloud is all around us. If we don't understand the first thing about a cloud, and we don't understand almost anything we need to understand, which is why which is a big factor for why all the climate predictions go wrong. Climate predictions go wrong because nobody knows how to, account for a cloud. We know how to account for carbon dioxide, we know how to account for ozone, we know many things, but we don't understand cloud cover. So we don't even know the sign of the change. Like we don't know whether it's going to increase the temperature or decrease the temperature. We don't know whether it's going to increase the rainfall or decrease the rainfall. We don't even know the sign, let alone the magnitude. Okay, so this is where the cloud research stands now. And India is a special place where we need this occasional cloud cover so badly. So instead of going this way, if it starts going that way or something, then we are in deep trouble. So we have to look for, changes in this and try not to make it happen. So any questions so far? I mean, if they're brief questions you ask, like detailed questions we'll keep to the end. If just some clarity question based on my talk till now. Anything? Is it going reasonably clear? Yes or no? Yes, it's going slow or fast? It's going okay? Okay, good. So we'll continue. Okay, so right now we've understood that clouds are all over the place and we need to understand them. So what happens to this raindrop guy we were talking about? He satisfied all these conditions and he became this. This white color means that he became 1 micron or something, 1 to 10 micron in size, and that got reflected, and there's a lot of 1 micron particle droplets sitting in the Earth's atmosphere, and these things are reflecting the sunlight. That's about all. It doesn't mean they're a raindrop. We'll call a person a raindrop when he becomes 1 millimeter in dia, or order of 1 millimeter. So that was easy because lots of people did it, all of them became cloud drops. Now comes the hard part, cloud drop to raindrop. Let's go back to this equation which I said you can integrate easily for the growth of the radius A with time. This I've approximated knowing some conditions as 2 into 10 to the minus 6 square root of t in MKS units. Okay, just plug this in and you'll see that to form to a 10 micron droplet, once you're in a supersaturated environment with lots of aerosol, let me come back to the aerosol thing. I said that if we put lots of pollutants in, we'll get lots more raindrops. Now see what happens to that. To form up to a 10 micron raindrop, it takes about 3 seconds. From 10 micron to 1 millimeter, which is when I'll call him a raindrop, by this equation it's going to take 3 days. And the cloud's lifetime is about an hour. So I can suggest one simple experiment for you all. If you go to a clean terrace, just put a camera facing the cloud. Okay, take a movie, long-term movie of it, for 3-4 hours. If you go and stand outside, look at a cloud, it looks like a static object. It looks like nothing is happening there. It looks like there is one puffy cotton ball who lives there, a gentle, nice cotton ball who lives there forever. That is not true. You keep the camera, you will see that it's gone away in like 1 hour or something. And another cloud may replace it, it may aggregate, it may separate. Lots of things are happening over time scales larger than when you're just viewing it. So do this over slow time scales. In fact, it will be nice to collect lots of such data and see how Indian clouds evolve over long time scales. So that is one thing I want you to do if you have interest in this. So this is not happening. A raindrop is not happening by this method. So then, if I so something has to happen to speed it up like crazy. Okay? So for that you need things like collisions, which I'll come to. If you have lots of pollutants, you make lots and lots and lots and lots of 10 micron droplets, but none of them grows. So you form more droplets, but you form more cloud drops, but you form fewer raindrops. So lots of pollution can suppress rain. It's not a brilliant thing. Okay, so the thing is that we know it's not taking 3 days. We know we are getting rain. That much we know experimentally. So we have to understand that therefore, within a span of a few minutes, they're all going from 10 micron to 1 millimeter. Large number of them on a rainy day are going from 10 micron to 1 millimeter, and they're given a few minutes. So clearly this equation is not doing the job. It's not by diffusion. So what's going on? So you have to ask that. So we can summarize it by droplets are growing too fast in real life. And we are not explaining this by our simple Clausius-Clapeyron arguments. This is famously called the droplet growth bottleneck. So this is an open question, the bottleneck question. So I cannot give you the answer to why it's growing too fast, but I'll give you some general pointers. So we are now talking about the cloud drop, who's almost a raindrop, almost becoming a raindrop, and how can it cross that bottleneck from 10 micron to 1 millimeter, or even to 100 micron. The next thing you can think of is gravity. You can say, oh, like, these guys are all falling. They're all falling, and then they will dash against each other. They will join together, they'll coalesce. And so, like, they can make bigger and bigger raindrops. So I made this little calculation, I'll come to that. But so I'm giving you some data here. Under very wet conditions, you have 10 to the power of 9, 1 billion cloud droplets of order 10 micron per meter cube of air. Per meter cube of air upstairs, where it's supersaturated, where it's cold. 10 to the power of 9 cloud droplets per meter cube. The liquid water content on this very rainy day can be as high as 5 gram per kilogram. That's a lot compared to, what we talked about on the ground. So these are all, let's say they're falling under gravity subject to Stokes drag. So like how a solid body falls through fluid, right? Falls through viscous fluid. What's the downward force? Why is it falling? Gravity. Why is it going up? I mean, what's the upward force? Buoyancy and drag. There's two forces which are pushing it up. So at some point it will reach an equilibrium and reach a terminal velocity. This you can write down by hand, just by knowing the Stokes drag, okay? So if it is going by Stokes drag, it will have a terminal velocity very soon. So these all are falling under gravity at some terminal velocity. I've asked this question, why don't they fall? Like, why do you see a cloud sitting there? They all should be marching downwards, right? Is that happening or not? The answer is, it's not happening at the rate you'll expect. It's not at all happening at anywhere near the rate you'll expect because of turbulence. And because this Stokes drag is a drag opposing the motion of the particle, motion of the droplet. And because of turbulence in a cloud, this cloud is not the puffy static ball. Inside it, there's angry turbulence going on. There's like huge storm going on there. Like anybody who's flown through a monsoon cloud knows this. Like I don't have to tell you this. Like suddenly you're thrown up and down by this innocent puffy ball. Okay, so then you're getting thrown up and down. The air in that region is going in all directions. You can imagine that. So there's a drag which actually pulls this droplet in all directions. So the drag faces is not necessarily downwards, and it's relative to that velocity. So most of the time the terminal velocity is relative to the turbulence velocity. So if you have a terminal velocity in millimeter per second, the turbulence has a velocity 10 meter per second, it's going to drag you horizontally. No way you're going to move downwards. So like it depends on where you're being dragged. So you have to write down the resultant of this in spite of the turbulent drag. Okay? And so I put a turbulent viscosity here instead of a laminar regular viscosity, and I've got a millimeter per second. If I put a laminar one, I'll get centimeter per second. So then to just drive home the point that this is an open question, Wilkinson is a famous cloud physicist, and he has written a paper last year saying that gravity is enough to solve the bottleneck question. I have solved the bottleneck question. So like if you have by chance, by some vague stroke of luck, if you have just a small concentration of very large droplets, if that luck happened, then gravity is enough for them to collide and make, baby droplets. So this is actually raindrops. This is what is Wilkinson's theory. But absent in that theory is how you by some luck got a concentration of big drops. Why would you suddenly get some small concentration of big drops? So like it's all ongoing work. So this morning in next year principal's office, I wrote down these equations. So I may have made a mistake. I didn't have a paper also. I did something. So like you guys should actually examine it very critically and come back to me with mistakes. So you can actually do back of the envelope calculations like this to understand about a rainfall. So then this is the terminal velocity. I have said what's the relative velocity of two drops. Okay. If all of them are 10 micron, what's the relative velocity? What's the velocity of this minus the velocity of that? Huh? 0. They're all falling at the same velocity. Then can they collide? Nobody can collide or coalesce. No way. They're all following their own paths, the same pictures just moving downwards. The only way they can collide if some of them are moving faster than others. And the bigger guys will move faster. So let's say one coalescence event happened, and so now I have one drop who's got twice the mass. Twice the mass means 2 to the 1/3 times the radius. So if I say m is equal to 2, it's like m to the 1/3 times the radius. M to the 1/3 a will be its radius. So then I subtract that guy's radius minus the terminal velocity of the first guy, and I already get a relative velocity which is not 0. It's small but not 0. Okay, here's my relative velocity. What's the mean free path? You can actually calculate a mean free path of these things. So like how do you normally calculate a mean free path of molecules in your kinetic theory? You'll take a molecule, draw a cylinder around it, and see that in that cylinder when is the first likelihood of the next molecule. All of you have done this calculation, no? You'll get something like 1 by n pi d square, where d is the radius of that thing. And what is n? Huh? Yeah, the number density of the molecules. So that it's exactly the same thing. It's the number density of the raindrops here. So that's why, like, because I vaguely remembered that cylinder, I could write it down this morning. So then you write this, and then I know what d is for a drop whose, so let us say m drops came together to make one big drop. So now I'm asking what is the history of that big drop. He's still a cloud drop, not a raindrop. I'm asking how is this big cloud drop falling. If I said there's only gravity, no turbulence, just coming down. Under those assumptions, this guy has a radius of m to the power 1 by 3a. So like I can write down what is the mean free path because I know the d based on the other things. So this is the mean free path, and this is the time of collision, which is nothing but the mean free path divided by the relative velocity. Okay? So then the distance it travels and the size it attains, the m, the size it attains, I can write down just as a sum of these things. Okay, and because I got internet connectivity, I could quickly check that this is a divergent series. But if I remembered my convergence divergence formulae from maths, I would have known that this is a divergent series. And intuition tells me that it should be a divergent series. Why? I shouldn't have checked internet for this. I should have known the answer. Why? Because there's no limit, right? Like the bigger and bigger it is, if I have an infinite distance to fall, suppose the atmosphere is infinitely long, there's nothing which should stop me from going down, down and down. So distance should not be a finite number. I'm big and I'm falling under gravity, right? So this is a summation. So every t seconds it will collide, it will become larger, then it will go faster and so on. So it becomes this very simple series. You can write it down and send me mail if I've written it wrong. Okay, so we're discussing that droplets are growing too fast. Turbulence, we have to ask whether it's the answer to the bottleneck question. So this comes, here comes the fluid dynamics. So till now we've built up the background, and from now on I can't, tell you all the equations, tell you all the story, but I'll tell you what's really happening in a qualitative way. So turbulence, is it the answer to the bottleneck question? We don't know. So last year Wilkinson said that we don't need turbulence, we need only gravity, so long as by magic I'm producing some big drops. And a lot of the community doesn't quite accept that. They are working on it, and they ask questions. So like all of us ask Wilkinson some hard questions which he finds it tough to answer. So because we guys, in science there's always a bias, like we are from the turbulence guys, and we don't want like a cloud to become a cloud without turbulence, right? No, I'm just joking. We want the right answer. So yeah, turbulence. So turbulence can increase collisions and therefore coalescence by a huge amount. This is the thesis by lots of people. To this argument, our group in ICTS has added a thing called caustics, and I'll quickly tell you what it is when we come to it. But first, let's discuss what is turbulence. First of all, turbulence is a very, very strange animal. Normally, it's not intuitive to understand what turbulence is. So we know that when I pump water from my, sump to my overhead tank, the flow in the pipe is turbulent because it has crossed a certain Reynolds number, where Reynolds number is the ratio of inertia to viscous forces. Okay? So it's just because it crosses a certain Reynolds number, it becomes this strange animal. And why I'm calling it strange is the following thing. So let's now forget about the cloud for a minute, talk about flow through a pipe. Okay? What is flow through a pipe? It's pressure driven flow, right? So I'm applying high pressure here, low pressure there. So if somebody is pushing me from the back, I'm going to walk in that direction. And that's what the water does. Okay, that's logical, right? There's a force and there's a, distance covered in the direction of the force. Now, I increase my speed. That's all I've done. I'm still applying high pressure here, low pressure there. Now what is happening inside my pipe to each water parcel? Somebody is going like this in a circle. In fact, all of them are doing this. They're all vortices, rotating like crazy. Everybody starts spinning like for no good reason like this. And then some of them are going backwards, some of them are doing that, when the net force is in that direction. So this is turbulence. So it's a very, very complicated thing. It's because of the forces that each parcel gives to the other through pressure. So pressure can do weird things like change their directions locally. On an average, yeah, I'm pumping water upstairs. I'm doing that. But I'm losing a lot of energy to this. I'm dissipating a lot because of this unruly behavior. Okay? So I can't tell you the answers to this very simply. Like if you work in my lab on stability for some 3-4 months, you may understand what turbulence is. But we'll take for now that it's, yes?
As opposed to this, what is an example of a straight line flow? Because you say simple thing that you observe is water, that itself is turbulent. So what is an example of something which is ideal flow?
Try pumping honey through your pipe to your overhead tank. Yeah, that will give you the answer. And for small scale things like particles, they see Stokes flow. They see so for a raindrop or a cloud drop, air itself is very viscous. It's like honey. So the raindrop as an individual is moving in a laminar situation. But the rest of it is turbulent. So yeah. So then it's all made up of vortices. So one way to think about turbulence, this is an artist's image, not a real thing, but is long strands of rotating, rapidly rotating spaghetti. So you think of them as all spaghetti of different radii, different rotation rates, angular momenta. They're all like rapidly rotating spaghetti like in this thing. And vorticity is the driver for everything. So the whole of turbulence has got vortices of different strengths. And you know, apart from just being, they're not just spaghetti, they're not passive spaghetti. They can merge to become bigger and stronger. They can stretch to become thinner and more powerful. They can cut and reconnect. They can make new and this is going on all the time. Like, in fact, vortex reconnection is one thing which, you know, huge numbers of groups in the world will study nothing except vortex reconnection. So yeah, so there's lots and lots of problems here. But this is going on in a cloud. Add to that my poor little cloud droplets who are being shunted around like this. And I'm calling them poor and little for a reason, because I want you to change your opinion about them by the end of this talk. The interesting thing is we always think of turbulence as something which mixes. I switch on, you know, my juice and it mixes all my honey, sugar, everything. And then I put on my washing machine and it mixes everything. Turbulence does something very bizarre to raindrops. So I'm asking, does turbulence mix everything? Does it make uniform everything? Here, this is a simulation of my colleague Samriddhi. So we have a two-dimensional box in which there's some turbulence, and these black dots are particles. Okay? The yellow color denotes vorticity. Okay? So just see what happens to the particles. I've started with a uniform distribution. It's as if I've put sugar, I've already mixed it in, and sugar is uniform everywhere. Now see where it's going. It's demixing. And this is because of turbulence. Is that interesting or no? Yeah. See, it's demixing like crazy. So like what's happening is in these regions, the concentration of droplets is going up a lot. So the mean free path will go down a lot. So collisions, all those things can happen a lot. So turbulence helps raindrops form. Turbulence helps raindrops form. These are just, some circle. We made a prediction that there should be no drops inside these circles, and that comes out correct. So this is basically what turbulence does to raindrops. It demixes. And that's because of their inertia. They're tiny, but they have some small inertia. So they can get churned, centrifuged out of vortices. They don't just follow the streamlines. And this you can actually, this whole calculation for a given vortex, you can write on a piece of paper. You can actually do that calculation on a piece of paper. So we've actually done this calculation on a piece of paper. And to cut a long story short, here's a vortex sitting inside, something that's just spinning like this, okay? And we've colored the droplets in two colors, green and red. So we have shown that there's a special radius here, inside which this centrifugal action will make the tiniest droplet have a much bigger chance of growing than a red drop. So if you're near a vortex, centrifugation acts like gravity, and it gives you like superpower to become a super drop, a big drop. Okay? So now I'll start the movie. As time goes on, all these droplets will spin around. And what I'll do is, if a red drop collides against a red drop and they join, the color will remain red. If a green drop collides against a green or a red, it will become blue. Okay? Blue or black, I've forgotten the color. So then you can see in the movie who grows. So if you see lots of big red drops in the end, that means the red drops have won. If you see lots of blue drops, that means the green has won. So let us see who wins. See? Do you see all those blue drops? So basically, almost no red drop has grown. These guys, because they're bigger, they're getting centrifuged out faster. Okay, so anybody who started close to the vortex has a much bigger chance of becoming a blue drop, and this is what we call caustics. I won't go into the reasons why. So we are giving a very nice way in which a small minority of tiny drops can become big drops just by being near vorticity. Yeah? Okay. Because I'm running out of time, I won't go through all the messy equations we solve. But this part alone would be Navier-Stokes equations, which is the equation of force balance for any fluid flow. Okay. Then in addition we have buoyancy, we have temperature fields doing their own thing, we have the vapor field doing its own thing, liquid field doing its own thing, and the liquid centrifuging out, and we have all of this, and latent heat coming in and changing the temperature. This latent heat part I want you to understand, because condensation is going on, and as condensation goes on, latent heat is released and the buoyancy is changing. The cloud is able to rise more by condensation, it's able to lift up more. So these are the equations we've written down. We found a new scaling which I won't explain. I'll just run this movie quickly, where we've done a 2D simulation of what we believe is happening in clouds. So we start out with 2D simulation, vorticity. It's a supersaturated environment, but the temperature is 0 degrees. It's sitting in supersaturation. There is a supersaturation of some number, and then the droplet number density is shown here. So here is vorticity, temperature, supersaturation, droplet number density. This is an unpublished result as yet. So you will see what happens in the movie. You see that the vortices are getting colder. Agree? Only the vertical regions are at a lower temperature than the rest. The supersaturation is remaining inside, and the droplet number density is all outside. This one makes sense, like everybody is thrown out of the vertical region. I showed you that movie for one vortex, but now I am doing an actual simulation with all those complicated equations. So then like this is gone out of the vortex. So outside you have high number density of droplets. Because I have high number density of droplets, the nuclei are all outside. So condensation cannot take place inside. Is this coming clear? So there's no condensation inside. So that remains cold, but outside, because there's condensation and latent heat is released, it's becoming hotter. So you're getting temperature differences and you're getting supersaturation differences in this. So this we believe is an important mechanism for creating buoyancy. And when I said, and this thing I won't go into, but this is without all that cloud effect, Mamul turbulence, and this is cloud turbulence. So we are saying Mamul turbulence is different from cloud turbulence. That's the message that we've done. This study is over. Okay. So then like this is the summary of all of this, and then I'll do 5 minutes on a big cloud or something and then stop, okay? Are you all getting tired? You're okay with 5-7 minutes more? Good, thank you so much. Okay, so then we now talked about, we're talking about this loop. We're coming into this loop right now. So basically, I said, oh, poor little things, little tiny drops, cloud drops. Now I'm going to change that story. So imagine a bunch of bacterium or, tiny little plankton in an ocean. The ocean, let's say, is very turbulent on a given day. So there's like huge turbulence, huge waves, and there are bacteria sitting inside it. Some of us who swum in a big ocean, we know, like we also get thrown around by the waves and all, no? What will happen to a poor bacterium? It will get thrown around. So the bacterium doesn't decide where to go. The ocean decides where the bacterium should go. So in other words, it's a one-way process. The ocean is the boss and the bacterium is the slave. So the slave does what the boss tells. Now I'm going to make you the case that this is a closed circle. There's no boss or slave in raindrops and turbulence. So there's turbulence in a cloud that pushes around the aerosol. So till now it's that boss-slave story, aerosol. The aerosols, some lucky ones among the aerosols have become raindrops according to the process we talked about, turbulence, gravity, whatever it may be, some diffusion. They've become raindrops. In that process, they've released latent heat, and that latent heat is released differently in different places. Because of that, you get a buoyancy which is not the same at all places. And that buoyancy helps it stay aloft, and this buoyancy creates turbulence. I showed you the picture that I said Mamul turbulence and this turbulence. Oops, I'm going the wrong way. Mamul turbulence and this are not the same. You can see that this cloud turbulence is much more turbulent in some sense. So that buoyancy is helping the turbulence not die. So the raindrops are keeping the cloud alive. This is the basic message. The cloud is not the master. The raindrops are also equally important to have this going. So I wrote a Rahim Doha here which tells about this. So who knows this Doha? Who knows Hindi? Sorry, this is my Delhi education. Okay. It says, Rahiman dekhi badhen ko laghun dijiye dari, jahan kaam aave sui kaha kare tarwari. So basically it says, when you look at a big person, this is meant for, human life. When you look, just because you're friends with somebody important, don't throw away your unimportant friends. Because when you need a needle, what will you do with a sword? So that's what it says. And it says, so I'm trying to say that don't assume that for this turbulence, the raindrops are unimportant. Okay, so now we talked all this about a single cloud and how this turbulence thing is kept going. Now, we want to ask, we said every cloud cannot become rain because you need all these other processes, coalescence, this, that, turbulence has to be strong enough, the number density has to be good enough. All those preconditions come, from here to here. So this is not an easy process. This we saw was a relatively easy process. So then, what happens to the cloud raindrop connection or the cloud rain connection? And this we are trying to solve by using big data. So Advay is a computer scientist who's a postdoc in our group. We have a monsoon group with all of these people. And we are trying to explore many things about the Indian monsoon, including the cloud rain connection. So he has done this fancy thing called Markov random fields, which I don't have time to explain, which isolates which actually shows you, the raw data won't show you any of this. This is India, it's too light for the people at the back probably. But you see this kind of cloud cover, and you see that rain is a subset of that cloud cover. So we're trying to understand what makes it a subset and why, and how these patterns change over the seasons, and can we make predictions or can we make general statements based on this. So this is a big area of work which all of us are involved in. So this whole thing was about clouds. In my group we do a little bit of experiments also, and only one PhD student, Kroor, the Ravichandran, the photo I showed you in the beginning, he is the only guy who did his PhD on clouds. The other people are postdocs. So I want to show you what the other PhD students are doing in the group, and I'll just give you one jhalak of that and then we'll stop. Okay, so this is Ganga Prasath. He looks at flexible filaments on fluid interfaces. So he's made this bubble and he looks at how filaments wrap around this. So this is like a problem in bending, elasticity, hydrodynamics, surface tension, everything. So we look at all these forces, we write down the equations. This is actually an experiment he performed on he just takes a plastic wire, bends it, leaves it on the surface of a viscous fluid, and he's asking how it opens. And we've written a universal theory which matches perfectly with this, and that's come last year in the physical review fluids. And so he looks at this, the flow around these things, how minimal surfaces are created, when these things will wrap around. And he also looks at particles with complicated inertial behavior. So this is right now a Fourier transform he showed me yesterday, which we have no idea how to take the inverse transform. So he's doing lots of things like that. And then Sumit Birwa, he's asking this very interesting question. Collision is a very hard problem. So we are now talking raindrops colliding. We don't even understand how a ball falls on a plate. We don't understand the nearby dynamics of that process. So he's looking at that. He just has a steel ball falling in a plate through a viscous medium. And we're trying to understand the near dynamics of that with, variety of methods depending on a high-speed camera. And then we're using various optical tricks, some new things like Newton rings and all to figure out what exactly is the distance. Because the theory says that there's no contact before a bounce. But we've already shown by electrical thing that there is a contact before a bounce. So this is Sumit's PhD problem. And Ritabrata Thakur, he is looking at the Bay of Bengal. So he has gone on a couple of cruises, and we have a collaboration with we have a big consortium of Indo-US consortium which looks at problems in the Bay of Bengal. We have access to 2 ships. So our Indian ship is called Sagar Nidhi. It's a brilliant ship. And they also have an equally good ship called Roger Revell. So then our students, like he went on the Roger Revell. Several of our students have gone on those cruises. They collect data like this, you know, temperature, salinity, density. They collect data along the ship path, and we're trying to understand how the bay affects the monsoon. And that's a very interesting problem in itself. And Rashmi looks at instabilities of various kinds. So this is a typical Kelvin-Helmholtz instability, but she's looking at it in an oil-water system with surface tension. So to end my talk, I will, I mean, it won't be correct of me to end any talk without thanking all my past students. I've written their present affiliation as faculty members. So all of these people are now in permanent jobs in various IITs and ISER and all. And these are the people with whom I've enjoyed working over the years, and a lot of my knowledge comes out of discussions, arguments. It's been a complete pleasure and a learning experience working with all of these people. These are my recent graduates. I'm calling him a recent graduate I worked on. I explained to you why. And Mamta is a postdoc in Brazil, and Sharath is going to join as a postdoc in IIT Madras. And that's all I want to say. Thank you for your attention.
Thank you for the wonderful presentation, ma'am.
Thank you.
I had a couple of questions. Recently, even in media and newspaper, we keep reading about government proposals and plans to take actions on something like cloud seeding. So,
Yeah.
and we were discussing on the effects of aerosols and pollutants. Are they not like two different sides of the same coin? If not, what would be the difference and what would be the relevance to doing such activities?
Two different sides of the same coin means?
You said increase in pollutants kind of deteriorates the rain formation.
Yeah.
And we have governments trying to seed cloud, if I understand it correctly, and bring in some more rainfall, especially in dry and arid areas.
Yeah.
So that would be my first question. Second question is, we discussed a lot about the effects of local turbulence in the clouds. How relevant and interesting is it to understand on a global level what are the causes for turbulence, and is there any study that is getting pursued on the same?
For what are the causes for turbulence?
Global turbulence,
Okay.
not locally, but globally, how does
Okay.
it drive, and what are the factors that cause them, and how the variations affect seasonal rainfalls and stuff?
Okay. So your first question was on cloud seeding. So like you can actually design particles like silver iodide and other such particles of certain diameter, certain thing, to actually induce rainfall by the cloud condensation process I told you about. Unlike, you know, pollutants which are very, very, very small. So you can design these things in order to induce rapid rainfall. And I mean, I personally am not a votary of it. I don't think we're solving problems by that. So maybe we can convince a cloud who won't otherwise rain to become rain. But like unless we look after our water cycle very carefully, these tiny, tiny measures are not going to really help us. And okay, like, you know, there may be a cloud band which is going from Karnataka northwards. And like we in Karnataka can cloud seed it and capture it before it reaches Madhya Pradesh or something like that. So yeah, we can do, you know, minor things like that. That's basically the cloud seeding idea, but it does work. I mean, people know how to make it work. So that's the first thing.
Coming to that question, like, but because the drift is from the ocean towards the land, would it not be like, is it not a feasible solution to make something like which is trying to condense and it's going to rain on the oceans, to directly capture it and make it rain on the, say, Indian subcontinent? Would that be possible, or because of the natural drift?
No, the clouds are coming from the ocean to the land.
So
Once they reach us, we've got them. So like there is a lot of rain in the Bay of Bengal. But mind this, like, you know, whenever you're messing with a very complex nonlinear system, it's incredibly chaotic, incredibly nonlinear. You know that butterfly flapping thing. You mess with it, you mess with the initial conditions, you don't know where it will reach. So it's not as simple as, oh, like I've convinced this cloud to come from the bay and rain over here. What if it doesn't rain over the bay? There's a particular salinity level, low salinity level required on the bay, so that the mixing layer in the Bay of Bengal is shallow. If it doesn't remain shallow, if it becomes a deeper mixing layer and that becomes more saline, then like where will the evaporation go at the same rate? So will we get rain? Will we get clouds itself? Are we messing with the system? So this is a very, very tricky question, which is why like I personally am against interlinking of rivers without thinking. You've linked it, you've stopped the water from going to the bay. That's a major thing you're doing without checking the consequences. I mean, that should be like what scientists study. Like you guys, when you come to your PhD and in your 30s and 40s, you may have partial answers to these things. We guys would have like died off by then. And that's when you're going to get the partial answers. But before, not waiting for all that, we want to interlink today. We want to take a political decision rather than a science decision. So this kind of thing is worrisome. So that's the thing with nonlinear systems. You never know what it's going to do if like man interferes in it. So that's one thing. Then coming to your turbulence question. So the thing is, like, take it from me as a given that anything in large scale is going to be turbulent. It will not be laminar. The laminar solution is unstable. The turbulent solution is the one it's the attracting fixed point for this nonlinear system. So you've studied about fixed points and all, no? Turbulence is an attracting fixed point. Laminar is a repelling fixed point after a certain Reynolds number. So anything on large scale is going to be turbulent. About the global patterns, there are people working on it. There's very large numbers of people working on it. We understand very little. See, so we know for one thing that, you know, in an El Nino year, something happens to the ocean currents and that messes up our monsoon. But that's not a given. Like there are, you know, drought years when there was no El Nino. So we don't know what happened. So then they say, oh, but wait, there's the El Nino is far away. There's one more thing called Indian Ocean dipole, which is like closer to the bay, and that thing is affecting the answer more than the El Nino. So then you start doing correlations with Indian Ocean dipole. You see some correlation. Again, it's not a perfect correlation. So it's not easy to write a global thing, a circulation model saying that does this and this does that. So that requires a lot more work. And you know, like a present day computer, I mean, the thing that we have, let's say, some in IITM Pune, they have 40,000 processor machine. In that machine, and abroad also, they're running like 40,000, 60,000, 1 lakh, that number of processors running in parallel. They can solve a small 1 meter box in a cloud, 1 meter cube. They can solve the turbulence in that exactly, because you need so many grids to resolve all the scales. Small scales are affecting big scales. We are not solving the global thing accurately. We're making lots of assumptions. When we do monsoon models and all, our grids are like 100 kilometers apart. So yeah, we need like incredibly faster computers to solve this thing.
Okay, got it. Thank you, ma'am.
When a cyclone forms in the air pressure, from a space station we just see like a vortex around.
Yeah, yeah.
So, but when we observe it, we just see a heavy downpour with a high amount of rainfall only at the coastal areas. Does this mean that it increases the supersaturation level in the clouds, or it depends on the turbulence caused by the cyclone in the clouds?
Okay, okay. So think of the cyclone itself as a big cloud. It's a big, big cloud, powerful cloud, which contains, and it will be very tall also. So that is coming into the land. So it is approaching the ocean from the land. Once it reaches the land, okay, the earth's friction is going to be, this is an engine, remember. This thing gets its turbulence, its energy to rotate from the latent heat and from everything that's going on there. So this engine is shut off.
Yeah.
So how far can it run?
Not much.
Not much.
Yeah.
So sometimes it runs across South India, but sometimes it dies off. So that's why like the effect is majorly in the coastal area. That's one thing. The second thing is there are instabilities. Something which kept it stable on the ocean, because of temperature contrast, it won't remain stable. So then it will break into things. So its death is very rapid once it reaches the land. So it's only a lucky cyclone who can run across.
Okay. So it does not have any link with supersaturation or aerosol? Because
it has less link because it's brought all the moisture and cloud with it.
Okay.
It's brought all the cloud with it.
Thank you.
Thank you for a good talk, ma'am. I have two questions. The first question is with regards to the turbulence that you discussed about. So you said the particles that are creating these turbulences or vortexes have very high moment of inertia. So what is the source of this moment of inertia? Do they pick it up from the land, or is it because of the churning that is happening within, or what is the exact source of this moment of inertia? That's my first question. And the second question is, what is the impact of the tidal effects due to sun and moon and other objects which are having strong tidal interactions with the earth? What is the effect of these tidal interactions on the clouds and cloud formation?
Okay, very good questions. All of you are asking good questions. Thank you for that. So to answer your tide question first, so basically, no, what was your first question? Where is the source of the moment of inertia? Yeah, that is basically because of Earth's rotation. So Earth's rotation is spinning these things, and you know, just like in a pipe, if you push me from behind, I'm not going to quietly walk forward. The atmosphere is not going to spin like in solid body rotation. Only the solid can spin in solid body rotation. It's going to do its own thing. So that's basically the source. There is Earth's rotation, and then there's power coming in from the sun. So like there's solar radiation, so there's lot of heating of the Earth's surface, and this thing like gives buoyancy. It causes evaporation, so effectively it creates potential energy by having light below. The ground gets heated very fast. So there's potential energy which can then be used to overturn. So all of these things are the sources. And then there's wind and ocean interaction. So wind can give to the ocean, ocean can give energy to the wind by shearing. So this interaction is also pretty large. So these are the sources. Now like in a tidal thing, like basically the tide can change the way energy is transported within the ocean. That's one important thing that tides do to the internal gravity waves. So when the internal gravity waves change how they're going, then mixing in the ocean changes. So the salinity and temperature contrasts in the ocean can be meddled with by the tides. And that has indirect effect on the evaporation.
So does that mean that it's an established fact that the speed of rotation of Earth is slowing down? Of course, it's a very long time scale to discuss, but does that directly affect the turbulence and cloud formation patterns over millions and millions of years?
I don't know the answer about how much it affects, but all I know is that we guys are doing it much faster. So like we guys are doing it on a century time scale. Like the Earth is a very, very massive object. Okay, the atmosphere is like, okay, if you have an orange and you look at its peel, that's like 1,000 times thicker for that orange than the Earth's atmosphere is. It's just such a thin object and it weighs nothing. It weighs nothing. Like in the Earth, in the core, inner core, outer core, the densities are so huge compared to densities on the thing. So even this slight amount of friction, and you have to account for how much we are gaining from the sun in terms of solar radiation. So that's why I don't know the answer.
Hello, ma'am. 2 years back, I read in an article like with an experiment, laser experiment, they have observed that the terminal velocity of a raindrop is higher than the theoretical terminal velocity. How can we account for it? Like, is it?
So, like some of them can gather momentum in different ways. You're saying it's higher at the surface than the terminal velocity.
Yeah. The theoretical terminal velocity, like what they calculate for 1 milligram of water or something.
Wow, I don't know.
I've read in, that's why.
I don't know. Like I don't know how it can get faster than it, unless it's propelled downwards by something. So like, if there's a turbulence downdraft, a very fast downdraft, then that can obviously bring rain down at a very fast rate. So then your terminal velocity is relative to that wind. So basically you have to have the terminal velocity relative to something. So it's just like an aircraft will land faster if it has a tailwind, right? So it's that. So if the drop has a tailwind, it can land faster. Otherwise, I don't see how it can. Because typically on rainy days, you have updraft, you don't have downdraft. So you can send me like what you read and we can worry about it. Yeah. Any other questions? Okay, thank you all for your attention.